Hi everybody, let's get started with the content for module number 6, where we'll finish out Mercury and launch into and cover the entirety of planet Venus. We left off talking about the planet Mercury and we're most of the way through. So we only have one video. The first video is the remainder of Mercury. We just have to talk about some of the more interesting surface features on Mercury that are going to help us put together a story of how Mercury evolved to its present state. So we have to talk about some of the unique surface features related to that. And then we're going to talk what we know about Mercury's interior, its magnetic field. We will talk about the fact that Mercury does not have an atmosphere, which is pretty much expected considering it's so hot and is so small. So it has low gravity and high temperature, which if you remember how planets lose atmosphere, that's the double whammy of bad right there. We'll end with our ideas of how Mercury came to be the way that it is today. So previously, we had looked at the bigger features like the calorous basin and the weird terrain and the intercrater plains on Mercury. Today, we're going to start looking at the smaller features. So just for a background context, just to remind yourself here that if you're picturing the planet Mercury in your brain, that the dominant thing that covers Mercury's surface are impact craters. But if you look a little bit closer, you'll start to see that Mercury is covered with lots and lots of very, very, very long, hundreds of kilometers long, several kilometers high cliff faces. So here you can see a very, very large cliff right here. Geologically, these types of cliffs are called scarps. So Mercury has scarps. They're technically lobate scarps, which tells us something a little bit about how they formed. It's from contractional tectonic motion. But we have these scarps here on Mercury. And they riddle the surface of Mercury. And as I was saying, they can be hundreds of kilometers long, as Enterprise Rupes is here. And they can be as high as several kilometers. So Enterprise Rupes is about 3 kilometers high. And while the naming convention for Mercury is that we call these scarps, they're all given formal names. So the Enterprise part refers to the naming convention that they're all named after famous ships, so U.S. Navy ships. So we have the USS Enterprise. That's also for you Star Trek fans out there, but it's actually a ship as well. And then the cliffs are given the Latin name for cliffs, Rupes. And I believe that's how you pronounce it. I've scoured the internet for the correct way to pronounce it. I'm going to assume that is as close as I can get it. It's either Rupes or Rupes. So what can we learn from these Rupes? Well, notice that you can see like these very, very large craters here, and the cliff is cutting across it. The scarp is on top of it. So we can look at the larger impact craters on Mercury, the ones that were formed during the late heavy bombardment, and we see that these scarps cut across them, which means that you had to form the impact crater first, and then you put the scarp across it. It also cuts over the intercrater plains, so this is starting to give us a time sequence of events of how things formed on Mercury. So we can have, say, the formation, we can have the late heavy bombardment, then the formation of the intercrater plains, and then the formation of these scarps. Then what we're using here is that relative dating technique called superposition. Now, these scarps are not unique to Mercury by any means. We saw these on the moon as well. And it was evidence that the moon is shrinking. It's going to be the same, we're going to make the same logical argument here, except we're going to see that Mercury has shrunk significantly. And I want to go ahead and take a look at some of these scarps since they're such an important feature on Mercury and they're so extreme on Mercury. Let's go ahead and take a look. So here you can see one of those light heavy bombardment impact craters, and here you can see Carnegie Rupes cutting across it. Over here, you have Beagle Rupes, and you can see the intercrater plains, and it's cutting across right there. Here's our Enterprise Rupes again, and you can see the white arrows are pointing it out. Here's a crater that formed afterwards. And you can see it's cutting through a lot of these craters here as well. And then using the Mercury Messenger data, they've been able to create a perspective view of what this would look like if you were actually flying over the surface. So here's what the Carnegie Rupes looking at this one right here in a perspective view. So you can see how tall those cliffs are. The coloration is elevation, where this is several kilometers higher than this. And just another just beautiful view from the Mercury Messenger mission. So here we're looking at the Vyasa and Stravinsky crater with the Beagle Rupes cutting right through it. And here we have the Svensdotter crater, and again, Beagle Rupes cutting through it. So if you really are curious about what the surface of Mercury looks like, here are some camera images with pretty high levels of detail, good resolution on the surface. Now, scarps are by no means unique to any unique to the planet Mercury. In fact, before I actually talk about a feature that is unique to Mercury, I really want to make sure that everybody gets this, because every semester, people always label the scarps as the geological feature that's unique to Mercury. Scarps are seen all over the solar system. We have scarps here on Earth. We have them on the moon. We see them on Mars. They're pretty much, if you have a terrestrial planetary surface, you're going to have these scarps, these types of cliffs. It's just on Mercury, they formed by a slightly different manner, and they're very extreme, which is why I was highlighting them. They're an important part of our story, but they are not unique to the planet Mercury. What is unique to the planet Mercury are these things called hollows. Let's take a look. We see the hollows. They're always on the floors of impact craters or on the rims of impact craters. So right here, you can actually see these pits that have fallen down or maybe were blasted out. We're not 100% sure on their formation yet. You can see these pits. If we really zoom in, you see these clusters of very steep walled, so straight down pits. They're not bowl shaped like craters. They are pits, kind of like a well. They always appear near crater rims and on crater floors. We don't see them in other places on Mercury. And these are truly unique to Mercury. We've not seen these on any other planetary surface, and they are very interesting features in several respects. One of which is you can see how they're brighter in color than the surrounding terrain. So brighter surface almost always maps to young surface. So this is telling us that these features are very young. We never see a crater that sort of obliterated part of them either, which suggests that these are very geologically young, perhaps even still forming today. Some of the ideas, like Mercury has lots of volatile things where if they get hot, then they'll turn into a gas fairly easily. So one of the ideas is being so close to the sun that you'll have a thermal wave penetrate deep enough to the surface, turn a lot of these volatiles into a gas, which will then explode out, creating these hollows. All right, so that's it for the major surface features I wanted to highlight on Mercury. I want to talk about Mercury's interior. This prior to the Mercury Messenger mission, which studied Mercury from 2011 to 2015 and absolutely revolutionized our knowledge of the planet. We thought that the surface or the interior of Mercury was pretty bland. We thought the interior of Mercury would be very similar to what we expect for all the terrestrial planets. We were very surprised to find out that it probably has the most interesting interior structure of all the terrestrial planets, which is telling us something very interesting about planetary interiors in general, and something very interesting about the formation of Mercury itself and the formation of planets in general. So what we knew before Messenger is that Mercury did have a core, a mantle, and a crust. We knew it had a magnetic field, which means that it had to have a core with a liquid molten layer, so you could drive the planetary dynamo. And we expected a mantle and a crust. We knew that the iron core was much larger relative to the size of the planet than, say, Earth or the other terrestrial planets. But we had no idea that it was as large as it truly is. So, how big is Mercury's iron core? Huge is the right word to use here. So the total radius of Mercury is 2,440 kilometers. That's from center to surface. center to 2,100 kilometers away from the center is all iron core. That's 85% of the diameter of Mercury. For comparison, Earth's iron core is 55% the diameter. So this is an absurdly large iron core. And there is certainly a layer in it that is molten. Uh, so it's likely that the outer layer of the core is molten, and I'll show you a few graphics of that soon. The inner layers may be solid. Again, we don't have seismometers on Mercury, so we can't suss that kind of information out using S waves and P waves, looking at the S wave and P wave shadows. But we know that at least part of it has to be molten because Mercury does have a magnetic field. So we have this huge iron core. Then what's above it? You have a iron poor mantle. Almost no iron is expected to be in it. And then you have a very, very iron poor crust, and you really only have about 300 or 400 kilometers of that material. So essentially, Mercury is a giant ball of iron with a very, very thin rocky layer wrapped around it. Kind of a strange planet, right? And more than that, it has a layer, very likely has a layer that we do not normally see. So we usually think core, mantle, crust. It looks like Mercury has core, and then before you hit the mantle, you have an iron sulfide, FeS, layer, and then you have a mantle, then you have a crust. How can we determine this kind of information? We don't have seismometers. What we do, and Mercury Messenger did this, is we can map out the gravitational field of Mercury, compare that to its rotation, put all that data together and to figure out what are called the moments of inertia for the planet. And there's a specific moment of inertia called the J2 moment. By the way, this is beyond what I expect you to know in the class. If you look down at the bottom, you'll notice this is all green. But that J2 moment, what that comes out to be mathematically depends on the interior structure of the planet. So we can use that information to figure out the interior density structure. And just so we can actually see a picture comparing, so this would be if we scaled up Mercury to be the same size as Earth and put the interior structure side by side. Here's Earth's solid inner core, its liquid outer core, and its mantle. Compare that to Mercury, solid inner core, suspected liquid middle core, then this weird iron sulfide layer, then the mantle, and then the crust. So the mantle and the crust are such a very, very, very thin part of it. If you're interested in more of this work and you want to read more about it, I put a link to the Nature paper by Stevenson et al. 2012. So with such a large iron core, Mercury gets to defy the expectations that we set for a planetary dynamo because Mercury has a magnetic field. That is a very, very weak magnetic field with a magnetic field strength 1% that of Earth's magnetic field. But the structure of the magnetic field, the fact that it looks like a bar magnet, we can map out the magnetic field lines, tells us that this magnetic field is generated by the planetary dynamo, where you have to have that liquid layer that's both convecting and made out of a conductor, and then you have to rotate it fast enough. So Mercury has a very slow rotation period. If you remember from the last time, a little bit over 58 days, which is more than the 50-day limit I put. So how can it have a dynamo? It's also, out of all the terrestrial planets, the smallest baked potato. It should be super duper cool. The trick is, or the trick that we suspect, the hypothesis that we want to test, we're sending another series of spacecrafts there, Bepi Colombo mission, to actually start to learn more about this, is that given that Mercury has such a huge iron core, that it being large enough, it still has enough of it that's molten, and it being so big relative to the planet's size that even though it's rotating slowly, it can still generate via planetary dynamo a very, very, very weak magnetic field. Now, if you rewind in time, this magnetic field would be stronger the further you go back into the past, because it would have been a hotter, and you would have had a hotter planet with a thicker liquid molten layer. And a really, really important thing to point out, so Mercury does not have an atmosphere. And this is what we expect. Think about how small Mercury is. It's the smallest of the terrestrial planets, so it has a low surface gravity. And it's very, very close to the sun, so the surface is extraordinarily hot. Now, if you remember how we talked about how atmospheres lose, or how planets lose atmospheres, then if you have the particles of gas that are moving about 1/6 the object's escape velocity, so if the average speed of the gas particles is close to the escape velocity, then a planet will rapidly, in about a billion years or so, lose its atmosphere. Remember that the thermal velocity of a gas, we're looking at how fast something is moving on average, a gas particle is moving on average. And being so close to the sun, it doesn't matter if you're a heavy element like, or a heavy molecule like nitrogen bonded together, so diatomic nitrogen, you can't hold on. Mercury just can't hold on to it. It has too high of a temperature, making the gases move too fast, and it does not have enough gravity to hold on to those gases. So Mercury lost its atmosphere. Uh, However, if you're a internet sleuth and you're interested in such things, you might see some people talking about the atmosphere of Mercury. No, it's not an atmosphere, it's an exosphere, which is technically a different thing. It's not gravitationally bound to the planet. Uh, and what it is we have the solar wind, which is a constant stream of physical particles, protons and electrons, which are smashing into the surface of Mercury, which will then splash off atoms, and then those atoms will get blown away by the wind, and we can detect those atoms as they're getting dislodged from the surface and blown away. And I have pictures of that down here. You can see the calcium and magnesium exosphere as it's getting blown away from the sun. And we have a graphic down here that kind of shows how it's going on as well. You cannot consider this an atmosphere at all. It's not gravitationally bound. All those particles rapidly escape. And it's, if you were to try to consider an atmosphere, it would be about uh, 100,000 billionths that of Earth's, which sounds like vacuum to me. And the final piece of the puzzle for Mercury is, how did Mercury come to be the way that it is? With this interior structure, those scarps, the intercrater planes, and things like that. So we do not have a great, well, we don't have a nice singular story like the lunar magma ocean hypothesis. We do not have enough evidence yet to really determine the precise evolution of Mercury. Messenger really helped us, but ESA and JAXA have a new mission coming up called Bepi-Colombo, which is going to try to figure out exactly what's been going on with Mercury, especially now that we see that it's such an interesting planet. It's so key to our understanding of how terrestrial planets form in general and how our solar system formed. But we do have two ideas of Mercury's evolution post-formation, and we'll track this by the formation of the intercrater planes, sort of like we use the lunar magma ocean hypothesis to track the formation of the lunar maria. So let's take the same idea, maria-like formation. So early Mercury, being really, really close to the sun, being impacted, could have melted down the surface, forming a magma ocean type thing, but being more massive than the moon, it would cool down slower. It's a bigger baked potato. So if it's cooling down slower, it's not forming crust as rapidly as the moon would have been, meaning that by the time the late heavy bombardment comes around 3.9 billion years ago, Mercury would have had a thinner crust than the moon. So we still have the same size of impactors coming in. They're smashing into the surface of Mercury, creating these giant impact basins, cracking the crust down to a molten layer underneath. And what would have happened then, just like with the moon, we would have had a lot of volcanism, except this would have been planet-wide, not just on one side. And it having a thinner crust, it would have been a lot more magma coming up to the surface. So it would have filled the impact basins and then overflowed them, running lava over a large swath of Mercury's surface, where it just couldn't go over other crater rims, having a giant flood volcanic activity, as we call it, which then it would have cooled and solidified, much like it did with the moon, except it wouldn't be contained within a basin. And that cooled solidified part would be our intercrater plains, which we know are volcanic in origin. So that's idea number one. Idea number two. So being more massive than the moon, it cooled slower and had a thinner crust. That part's still common between both of us. So the late heavy bombardment comes along, and we have an object that's just hotter and more molten. And you have to remember these late heavy bombardment impacts are super energetic. So they hit the surface of Mercury, and they hit with so much energy that they don't blast a bunch of rock. What they do is they pretty much melt everything that it ejects. So it turns the crust back into lava and throws it about the planetary surface, causing sort of a flood activity volcanism again. We have fluidized ejecta made out of lava, which then cools, solidifies, and formed our intercrater plains. So finally, we have two ideas of how we could have formed the intercrater plains, but we haven't leveraged the most interesting piece of evidence. So post late heavy bombardment, post the formation of the intercrater plains, we know that we formed the scarps because they cut across both of those objects, the impact basins and the intercrater plains. So how do we form those scarps? And here we have to leverage the idea that Mercury has an absolutely huge iron core. So as things cool, they shrink, they contract. Metal will contract a lot as it cools down. And having such a large iron core, as that iron core cooled and shrunk, the entire planet of Mercury would have shrunk with it. In fact, the radius has decreased by a projected 7 kilometers. So we had this surface area, then we let the planet shrink by 7 kilometers. We had too much surface area. What's going to happen as the planet shrinks? Well, it's going to push against one another and it's going to pop up and form these scarps. Another way to think about that is you put a raisin out in the sun, or you put a grape out in the sun, and as it dries, it shrinks and it forms wrinkles. Those wrinkles would be the scarps, except now we're doing it on an entire planetary scale. So Mercury shrunk. And the idea with this is, with it shrinking so much, any of those cracks that would have been formed in the crust, as Mercury shrinks, it's going to squeeze those cracks tightly together and close them up, which means that Mercury actually has been geologically dead longer than the moon has. Which is kind of a cool way to think about it. It also gives us the scarps that are forming. We also see that Mercury is still shrinking we're seeing the formation of new, smaller scarps, just like we saw with the moon, which is really, really cool. And I do want to just point out, if you're interested, especially as an extra credit thing, there's the ESA plus JAXA, so the European Space Agency and the Japanese Space Agency, have a mission called Bepi Colombo that's currently en route to Mercury. There's going to be 2 satellites. And the entire mission, or one of the major mission goals, is to determine Mercury's magnetic field, its magnetosphere, and look at its surface and interior structure. It's slated to arrive. It's scheduled to arrive to Mercury in December of 2025, and it has a long route to get there. It actually decreases its velocity a little bit so it could spiral inward towards the sun, and a flyby of Earth on the 10th of April. All right, thank you for tuning in for this last video about Mercury. That was a little longer than I expected it to be, but I was having a whole lot of fun talking about all these cool details of Mercury. I really hope that you enjoyed it. I am fascinated by this planet, and I can't say that I was 5 years ago.